All right, we are back with Unit 2, Topic 2. This is like the second part of that video. Um, I had mentioned before that we were going to sort of break this topic up into discussion of ionic situations, and then today we're going to be talking about covalent situations. So, um, once again, here is the objective from the AP course and exam description. And so what we're going to be talking about today are covalent bonds. We're going to be talking about bond length and bond energies, okay, having to do with covalent bonds. Okay, so I need to skip through quite a lot of these slides here to get to the end. All right, so I've stolen a couple of slides from 2.1 actually because they're still relevant for us. So during the 2.1 video, I talked a little bit about why covalent bonds form, how they form. And the story is that it is complicated. I'm going to try to go into a little bit more detail now to talk about sort of why covalent bonds form, to give us a little bit of a better understanding. Ultimately, the answer is still going to be the same. The overall energy, electrostatic potential energy of the system decreases when a covalent bond occurs. And so what I would like to do is I would like to look a little bit more at, an explanation so that in our heads we can explain it a bit better. Okay, so a lot of times people like to use this term stability to explain why bonds form. Okay, the atoms will bond because it'll be more stable. That is not the best way to phrase things, okay? And it's not precisely correct, okay? The reason that atoms bond, okay, is to minimize their electrostatic potential energy, okay? And this image over here, I want to talk a little bit about this and see if we can really understand what this means. So this is just a model of some hydrogen atoms. I want to talk a little bit about what this model even is showing us here. So we have this plus sign in the middle. That's clearly meant to be the proton, right? Hydrogen having atomic number 1. But what is all this red, right? Because hydrogen atoms only have 1 electron as well, right? So, what exactly is this red stuff here, or pink color? How I interpret that is that the red is kind of like negative charge density, okay? So it's supposed to represent sort of the electron, but remember that electrons don't really behave like individual particles, right? They behave more as like amounts of energy that have a negative charge, if you will, okay? So in this image here, what we're seeing is that when hydrogen atoms are sufficiently far apart to have no interaction with each other, okay, so separate, the negative charge density around the proton, the positive charge, is sort of equally distributed around the atom, right? And picture this almost in 3D, right? So it'd be like a spherical, somewhat equal spread of the negative charge density. Obviously, it's a bit more concentrated towards the nucleus, right? Protons and electrons are attracted to each other, so the electron, it's in the first energy level, it's in the 1s orbital, right? And so more often than not, it's going to be found closer to the nucleus than farther away. But we're starting to get into the weeds here. So let's just take the idea that these red dots here represent like negative charge density. Okay, and the more dots, the more dense; the less dots, the less dense. Okay. As the atoms begin to move closer towards each other, what happens is a lowering of the electrostatic potential energy. Okay. The 1s orbital has room for 2 electrons, right? It can hold 2 electrons, right? We could have 1s2, okay? Hydrogen only has 1 electron, though, okay? So when you get 2 hydrogen atoms together, by sharing the negative charge density, what they are essentially doing is they're lowering, and this is the hard part to convey, they're lowering their overall electrostatic potential energy by being close to each other and allowing the negative charge of the electrons to feel the attractive force of both nuclei. Okay? So, and that's what the bond is. The bond is not some sort of special, structure that forms. The bond is literally just the electrons arranging themselves in a way where they're in between the nuclei, and you would have to put in some work to separate them, because they're in a lower energy state. They're in a state of lower electrostatic potential energy, while the two hydrogen atoms are in this configuration. This is what a H2 molecule is, or molecular hydrogen. It's these two hydrogen atoms that have come together because the electrostatic forces drove them to do this. It was a lowering of their electrostatic potential energy. Ultimately, that is the explanation for all of covalent bonding. It's a lowering of the electrostatic potential energy. It's something that is hard to explain, hard to describe, hard to comprehend. Some of the best scientists out there aren't great at communicating what they might understand in their brain. So, and that me too. I'm in that category as well. So, as long as you can hold on to that idea, though, that covalent bonding is a lowering of the electrostatic potential energy due to the arrangement of the nuclei and the electrons between them, that's good. Okay, that not good enough, but that's what we need to be thinking of. Okay, and being able to perfectly describe exactly what's going on here is a hard task that we're going to work on throughout this unit. Okay, we're going to be talking about covalent bonding a lot more than just today. Okay. Here is another example of that, and I wanted to show you another example other than just the hydrogen, just to get another look at it. Okay, so I've got these two elements here, chlorine and argon. Recall that chlorine is number 17 on the periodic table, argon is number 18. Chlorine is a halogen, highly reactive elements. And argon is a noble gas, highly unreactive elements, right? Here are the Bohr models of these two elements. You'll see here that they've actually labeled the electrons as either s or p orbital electrons. So chlorine, right, has 7 valence electrons, right, whereas argon has 8, okay? Now, if I were to ask you this question, right, pure chlorine can be found as a molecule, right, Cl2, but argon does not bond. If I were to ask you why, a lot of you, most of you, would be very tempted to say something like this. Chlorine only has 7 valence electrons and needs 1 more to satisfy the octet rule, right, to get to 8 electrons, 8 valence electrons. And while that isn't wrong, it's not the best explanation for why chlorine bonds with itself, just like hydrogen does. It's not the best explanation, okay? The reason that 2 chlorine atoms will join up and form that diatomic molecule is exactly the same reason that hydrogen atoms do the same thing, okay? If you look here at this drawing or model here of 2 chlorine atoms, there is a open spot for a 8th electron to occupy here in this 3rd energy level, okay? And if you imagine having 2 chlorine atoms, right, when they are separate compared to when they are together, it's when they're together that their actual overall potential energy, electrostatic potential energy, is at a slightly lower state. The electrons here can sort of float themselves in between the chlorine nuclei, and the electrons here can feel the attractive force from both nuclei rather than just one. It's a lowering of the electrostatic potential energy, very similar to what goes on in H2. Okay, but enough about that for right now. We'll discuss covalent bonding more throughout this unit, and we'll get some more exposure to it as time goes on. All right, so let's get into what really is the objective here for this topic, which is to talk about bond energies and bond lengths. This is a slide that I stole from the 2.1 notes as well. We can prove that covalent bonds are a lowering of the potential energy because we can break the bonds and it costs us energy to do that, right? So if breaking the bond costs us energy, then forming the bond would lower the energy, right, or reduce the energy. So I talked about this in the last, or in 2 videos ago, I think. You can take a molecule of methane and you can peel the hydrogens off one by one, and you can actually experimentally determine how much energy is required to do that. So you come up with sort of an average bond energy for a carbon-hydrogen bond, right? If the amount of energy that we spend peeling each hydrogen off one by one, that's like breaking one carbon-hydrogen bond, one at a time. And so if you take these values here and average them up, you come up with the average bond energy for a carbon-hydrogen bond. You can actually do this for lots of different bonds, and scientists have, okay? So specific bond energies will vary from molecule to molecule. You'll see here how these bond energies are actually wildly different. I mean, look at this one. Just taking one carbon-hydrogen and taking them apart doesn't cost you as much compared to, say, when there's 3 hydrogens connected to a carbon and you take one of them off. It costs you a lot more energy to do that than it does that. So the bond energies can and will vary from molecule to molecule, but for our purposes and for most scientists' purposes, having an average bond energy is usually good enough, okay? And so this table here, which you can find in your book, not sure exactly what page it is, but it's table 8.5, you can find this big list of average bond energies, okay, in kilojoules per mole. So this will be useful for us when we do some calculations where you need these bond energies for the homework for this topic. One other aspect of covalent bonding that you're supposed to know about, according to the AP course and exam description, is how double and triple bonds impact the length and energy of a bond. So a single covalent bond is a shared electron pair between 2 atoms. If you have a double bond, that would be 2 electron pairs. What happens is the nuclei are sort of bound closer together. The bond length shortens a bit. And you can see that here in the data. A single bond between 2 carbons has an average bond length of 154 picometers. When that goes to a double bond, that shrinks up a bit to 134, so about a reduction in 20 picometers. And then as it goes to a triple bond, as you add an additional electron pair that is sort of bringing those nuclei even closer together, right? Remember that those electrons are negatively charged, right? So the positively charged nuclei, they sort of tighten in a bit around that triple bond. You end up with a further reduction down to a very short bond, 120 picometers. Okay, the actual values here, guys, are not important, but what you're supposed to know for the course is that as bond order increases, so like from a single to double to triple bond lengths shorten. Okay, and the bond energy, the amount of energy you would have to spend to break that bond, increases. Okay, so like I said, when the bonds shorten, think of it as them like sort of tightening up and becoming harder to break. Okay, and this is true for carbon-carbon bonds, carbon-oxygen, carbon-nitrogen, and I'm sure other types of bonds that can have single and double bonds as well. Okay, all right, and so the last thing that I need to talk about in this video, it's going to be a relatively short one actually, is how to calculate what is called the enthalpy. or specifically the change in enthalpy of a system. So enthalpy is kind of a hard term to define, especially for us. We don't have a ton of vocabulary that, what am I trying to say here? Until you take physics, or until we get into like the thermochemistry unit, here's how I'm going to define enthalpy for you, okay? Think of it as just the amount of energy in a system, okay? So what we're going to be doing in this homework set that you're about to start here very soon is we're going to actually be calculating the change in enthalpy around like a chemical reaction, okay? So you take some chemicals, they react to form new chemicals, right? It's a chemical reaction, chemical change. The enthalpy is going to change, okay? And generally speaking, okay, you can see here, generally speaking, reactions will occur when the net enthalpy is negative, right? And remember, from the perspective of the system, if the net enthalpy is negative, that means that during the reaction, energy was released or energy was lowered, right? From the system's perspective, right? Energy was released. That's generally why chemical reactions occur, okay? When the system lowers in potential energy as a result of the reaction. So what we're going to be doing is calculating these delta H's, or these changes in enthalpy. And it's actually really simple. This formula looks very complicated, but it's really not. Basically what you do is you add up the bond energies of all of the bonds that are present in the reactants, so the things that you start with, the chemicals you start with, and you subtract the bond energies of all the bonds in the chemicals that you formed, so your products. So once again, you take your bond energies of your reactants minus your bond energies of your products, and usually, if a reaction actually does happen, then this is going to end up being a negative number, meaning the energy released is greater than the energy required, right? If this is a larger number than this, then this overall number here should be negative, right? Smaller number minus a bigger number. Don't worry too much about what N and D mean. We'll probably do an example of this in class, okay? Okay, also in addition to doing an example in class, there's a really thorough example of how to do this in your textbook on page 324, 325. And you'll notice an important phrase at the end of that example, which I want to bring up, okay? At the end of the day, the answer to the example is negative 1,194, okay? But the way that that's interpreted, okay, let's just read this last sentence here. Since the sign of the value for the enthalpy change is negative, this means that 1,194 kilojoules of energy is released per mole of this molecule formed, okay? So as this is forming, energy is being released, okay? And it's due to, once again, if I go back here, the amount of energy required to break the bonds is not as big as the energy released when new bonds form, okay? All right, I believe that's it for this video. Sorry I don't have this published as soon as I would like. Now that we're sort of back from fall break, I should be able to get on a schedule where I've got the videos out 48 hours in advance. I realize this is more like 24 hours, so I do apologize about that. Hopefully things will get a little bit better here in the near future. All right, thanks for watching, and I'll see you next time.